Okay, so Khronos does quite a lot of standards, so I'm going to show you another standard and what we use it for. So SYCL is another Khronos standard for a slightly different situation. So there's quite a lot of crossover in all of these things, so it maybe gets a little bit confusing. But what SYCL is for is it's directly a programming model. And I'm going to talk about it in the next presentation. What I'm going to focus on first is what we've done with TensorFlow. So what you will have seen this morning is things like NNEF and OpenVX. So what that's for is for taking a network that you've trained in TensorFlow and putting it into something else. What I'm going to talk about now is actual TensorFlow, right? So this is open source TensorFlow. You can check out TensorFlow and you can run it using a SYCL compiler on a variety of different devices. So you can build, with this, you can build TensorFlow and run on any accelerator that supports the right OpenCL features. So it's kind of a layer. SYCL sits on top of OpenCL. SYCL is an open standard from Khronos. OpenCL is an open standard from Khronos. Now, you may need to do some adaptation of some operators to achieve the right performance on each device. But it's all open source, so you can do that yourself. So I'll give you some performance figures, and you can see that there's some optimization still left to be done in some cases, but it runs everything. That's the advantage of it. It's the same source base as with the CUDA version. We're just providing an open standard alternative. This work supports training and inference, and it supports all of the tools of TensorFlow, like TensorBoard. You can run Keras on top of it as well. So this is separate from projects that extract TensorFlow graphs and run it on something else. That's what NNEF or OpenVX would be for. This is when you want to run full Python TensorFlow itself. And I'm going to skip the marketing slides because you've seen them. So SYCL TensorFlow, this is kind of a progress report of where we are in terms of TensorFlow support. So inside TensorFlow, there are 873 operations, of which 360 work on CUDA. The rest of them, you probably don't want to run on a GPU. You probably think, why don't they run on the GPU? They're things like loading from a file or printing something to the screen, which you're not going to run on a GPU. So about 360 operations at last count run on CUDA, of which 269 run on SYCL. So really quite a lot of features there. I've actually compared it with some other kind of smaller neural network systems like Android NN, and they support much, much smaller number of operations in TensorFlow compared with what we do. So it may well be that the network that you've got fits on something like Android NN, that those features are enough. But if you're doing something more advanced, or for example, if you take TensorFlow and customize it, because it's open source, you might add your own nodes, then SYCL enables you to use that. So for example, this is TensorBoard. This is a kind of debug feature inside TensorFlow. I'm not really a machine learning expert. I'm more of a programming models person. But this, you can at least understand. It's like a web page. You can connect it. So I think this is running on, I can't remember if it's running on an AMD GPU or if it's actually running on a little, we've got this running on a little ARM Mali board. But the same features that you run on an NVIDIA GPU run on GPUs, accelerators, maybe FPGAs from other people. And I'm told Keras works as well. I haven't tried it. This is where we are in terms of performance. So I did warn you, we've not done all of the optimization on all of these devices, so we are not quite up to NVIDIA performance yet on complete networks. I was showing these numbers earlier. So you can see on this board, it's got a very low power GPU. We do get acceleration on real networks compared with, this is the little cores and this is the big cores. So we do get performance improvements by running it on the GPU. And yes, full TensorFlow designed to run on a big data center does actually fit on a board this small. You can get it for $250 or something from Amazon and run all of this stuff. And then on the top, we're comparing an equivalent, roughly equivalent AMD GPU, or two AMD GPUs, a FirePro and an R9 Nano, which is slightly old compared with a similarly spec'd NVIDIA GPU on training. And you can see we're about a quarter to a third of the performance of an equivalent GPU. That's without having done any real specific optimization for AMD. What you can see, what the AMD does work very well, and I'm going to explain why, is when we have the source code, we actually do better than NVIDIA on a lot of things. So if you look here, these are all the eigen benchmarks, where we have the source code, we're recompiling them for AMD. Actually, in a lot of cases, we get twice the performance of an equivalent NVIDIA GPU. And that's because the AMD GPU seems to have twice the bandwidth for a lot of things. On random memory accesses, it's worse. So where we're falling down on performance currently is on the matrix multipliers and the convolutions, and that's not a compiler issue, so that's nothing really to do with SYCL. It's not a SYCL feature. My next slides are going to explain how we deal with that. But in terms of SYCL as a programming model, actually we're beating CUDA on an NVIDIA GPU. It's what we are not beating is the hand-optimized assembly of cuDNN and cuBLAS, and that's not a programming model issue. Again, on this board, these are the eigen benchmarks running on this board, and we're getting big speed improvements compared with the CPU. So it's pretty good for running your own code. It's just what we're missing is matrix multiplying convolutions to cuBLAS and cuDNN levels of performance. But we're working on that. This presentation is partly about the work that we're doing and the progress that we're doing. So if you want to get it, CodePlay, because my company's compiler does actually have an implementation of SYCL, which you can download for free. We've got a community edition. You can download it for free. There is an open source implementation called TriCycle. It doesn't support full-on TensorFlow yet. It supports some things. It's getting better. You need to get hold of, obviously, for those there with the ARM boards, we support both ARM, x86, Linux, Windows, but you need to get the right OpenCL implementation. We really push OpenCL implementations with this, so the features is quite demanding to be able to run all of TensorFlow. So we've worked with some of the vendors, like ARM, to make sure that their drivers support that, but it means that you need to get the latest drivers to be able to do that. So I think with Intel, if you want to run it on an Intel GPU, it's the Neo driver, which is open source but very recent. With ARM, you have to go to their website and get the driver. And even then, I think there's a little bit of a problem. I think we need to get them to update it slightly. But then that's it. You check it out. You compile it. When you compile it, it asks you, do you want to build it for NVIDIA GPU? Do you want to build it for CPU? Or do you want to build it for OpenCL? It actually asks OpenCL, not SYCL. And if you select OpenCL, then it just goes through all the stages. It finds out what GPU to optimize it for. And then produces a Python package. And there you go. Got the whole thing. So very easy to try out. Right, so because this is quite hardware focused, this conference, I kind of have to explain where the network, how it maps a neural network to the hardware. So this is a simple network. I think it's AlexNet. And what you find in these networks is you have convolutions and you have matrix multiplies, and then you have a whole load of other layers, activation layers and stuff like that. The convolutions go to SYCL DNN. That's a slight lie. It won't be a lie. Currently, it just goes to some hacked code, but it is going to go to this new thing called SYCL DNN, which is going to be open sourced extremely soon. But it will go to SYCL DNN, and then the SYCL DNN has got SYCL code, but we could plug in, because it's open source, you can just plug in to use specific convolution hardware. We don't do that yet, but because it's open source, you can do that. And then with the matrix multiplies, it goes to SYCL BLAS, and then that could go to matrix multiply hardware, but right now it goes to SYCL code to OpenCL. So those are the two areas, SYCL DNN, SYCL BLAS, where the device-specific optimization really has to happen. And then for all of those other layers, so I mean, this is only like 2 or 3 ops or something within TensorFlow. So for those other 250 operations, they go to eigen, which goes to SYCL code and goes there. There are some device-specific optimizations we need to do in eigen. It's a small number. Maybe I'll go into it, but it's a certain class of operation. I think it's the later slide where I go into that. So basically, this is TensorFlow on CUDA. So this is what TensorFlow looks like as an architecture when on CUDA. A Python client at the top. Most people use the Python interface, but there's a C++ interface and a C API. And then you've got over 800 of these TensorFlow tensor kernels, which sits on top of eigen tensors, which sits on top of the CUDA compiler. And then you've got some matrix multipliers and some convolutions, and the matrix multipliers sit on cuBLAS, and the convolutions sit on cuDNN, and they are hand-coded assembly for NVIDIA GPUs. So what we're doing is we're making a simple replacement at the bottom of the stack to enable this to work. So we're using a SYCL compiler at the bottom, either Compute CPP or SYCL, and then you've got SYCL BLAS and SYCL DNN that's just replacing the cuBLAS and the cuDNN. I'm switching between the two. That's all we're really changing. And so what that means is this is the same source files. It's all controlled with ifdefs. So it's not a port, as in, it's not a rewrite or anything like that. You're not plugging in some different OpenCL interface. It's all the same source files, so all of the same logic is there. And that means we can maintain it so that we can keep it up to date. So what do we need to do to get the performance up? That's one of our main targets. We need to support more hardware, of course, but we really need to get the performance up to be fully competitive. So SYCL DNN, we've discovered, is the highest impact on performance. I think I've not got numbers showing you what that looks like in a network, but it's a big impact currently. So when we look at profiles, you can see that the convolutions are generally what's taking up a large amount of time and what's a problem on non-NVIDIA hardware. And what we've discovered, and I'm going to show you in some numbers in the next slide, is that you need to adapt the algorithms quite extremely to different sizes and shape of convolution. Or alternatively, we need to make use of hand-coded assembly. So we need to be able to integrate the kind of hand-coded assembly that NVIDIA's done with cuDNN, but for all of the different sizes and shapes of convolutions. And it does vary extremely. I'm going to show you this. Some convolutions actually make use of matrix multipliers. So some convolutions are actually, there's a thing in neural networks which mystifies me called one-by-one convolutions, which actually are a matrix multiplier. I don't know why they call them one-by-one convolutions, but they like to pretend. And then there's other things like the Winograd technique, which is a special technique for optimizing convolutions that actually is a matrix multiplier. It's like 8 matrix multipliers, something like that. So we also need to optimize the matrix multipliers. So when I said it's the convolutions that take most of the time, actually some of those convolutions are matrix multipliers. So getting really good matrix multipliers for each processor architecture is vital. I also lied a bit about SYCL BLAS. What we actually use is the eigentensor contraction, because that's actually what's in TensorFlow. But we're in the process of replacing it with SYCL BLAS. SYCL BLAS is already open source. We did it in conjunction with some academics in Madrid, in Spain, that are experts in BLAS algorithms, and so they've done various papers on it, and you can have a look at that. What it does is it handles matrix multipliers, and it adapts the algorithm to different processor architectures and different sizes and shape of matrix. So this is something else that we've discovered, as well as the convolutions. The matrix multipliers in deep learning are extreme. They are extreme variations of size and shape. So you'll see something that's like 15 by 8 million or something as a reasonable sized matrix, which you wouldn't see in other situations. But in deep learning, they do come out as these extreme sizes and shapes, and you need to adapt your algorithms for that. So when we looked at the NVIDIA ones, I found that in a typical neural network, even a really small neural network, NVIDIA is using about 5 or 6 different matrix multiply kernels for different situations. So we actually use C++ templates in both SYCL DNN and SYCL BLAS to adapt the algorithm to different sizes and shapes, as well as different processor architectures, because different processor architectures vary massively for these. And then in Eigen, where we do all of the rest of the deep learning stuff, all we need to do is port the generic algorithms to each architecture. So one of the generic algorithms is a component-wise operation. It's a posh name to call it an algorithm. It's just take this one and output that. So each element of the tensor is completely independent, right? So it's trivially simple, except that what you found is loading the data on different GPUs varies to do it most efficiently. So some GPUs you want to load 4 words, however many bits that is. 128 bits. You want to load 128 bits at a time on each thread, whereas others you only want to load 32. And a strange one actually is the Renaissance hardware that I was showing over there, the vision processor. You want to do it the other way. You actually want to transpose the order in which you access the data. And that's probably true of quite a few DSPs as well. So we've got to do the component-wise operations, adapting access to the memory. Reduction operations. So eigen has a generic reduction operation. So if we're going to do sum up across an array, or more likely a partial reduction, where we're doing things like max pooling or average pooling, all of those things, you say to eigen, do a partial reduction on this data, and here's the operation. And this is something you can do in C++. You can define a generic algorithm which is going to be good on a parallel processor, and then you can say what the operation is. So you can say max pooling, average pooling, and define average in one place and pooling in another place as a partial reduction. And that does mean that we only need to change in one place where the algorithm changes for each new processor. We need to do shuffles and chipping where we're moving data around randomly, which is horrible. It really, really kills a lot of parallel processors, but I'm afraid it does happen a bit in deep learning. And tensor contractions is a posh name for a matrix multiply, but eigen has these tensor contractions. Actually, we beat the CUDA tensor contractions, but they're not as fast as cuBLAS, unfortunately. So the source code in eigen is actually shared between CPU, CUDA, and SYCL. So if you compile eigen with a CPU compiler, it will give you vectorized CPU multi-core code. So it entirely works within C++ header files. If you compile eigen with a CUDA compiler, it gives you CUDA GPU code. And if you compile it with a SYCL compiler, it gives you SYCL OpenCL code. So it's entirely handled within these header files, and it adapts to different systems, which is why when you want to optimize TensorFlow for your system, you actually have to check out the source code and compile it for your system. And it will actually look at the processor in your system and the GPU and try and work out how best to do it. So it's a compile time thing where you optimize all of this stuff. So these are some numbers that we've got for SYCL DNN, which will be open. It's not currently open source. It's going to be open source very soon. What we're showing here is it's 5 different algorithms for convolutions. So these are standard algorithms. So these are forward convolutions. So you use these in inference. And we've got direct, which is just trivial. It's just a for loop over the neighboring pixels or tensor elements. Direct tiled, which does a very, very simple tiling. A system called IM to col, where you convert a convolution into a matrix multiply. So you copy all the data into a new format. Then you do your matrix multiply, and then you copy it back. Some of them, remember, one-by-one convolutions are a matrix multiply. So then we actually do the matrix multiply. And then some of them we use the Winograd technique. And the colors have come out horrible in this one. I thought I had a better color one, but anyway, right, okay. Copying from one place to another. So what do you notice? AMD, Mali. What this graph is showing is the color that's furthest out is the fastest algorithm for that device. And you can see the numbers are up to 3 times, 2 or 3 times difference in performance. So by choosing different algorithms, up to 3 times. And there's some weird ones, like the matmul is sometimes slower than the direct convolution, even when it should be a matrix multiply. And Winograd works in a very unpredictable set of cases. Like it should work really well on the AMD one and badly on the ARM one, if you're thinking about it, because it's doing a complicated matrix multiply, except for some reason it's the other way around. This direct tiled one works quite well in ARM. But next, these are forward convolutions. If I show you training convolutions, the graph looks totally different. And there's actually 2 different kinds of training convolutions. I'm only showing you one of them, and the other kind of training graph looks totally different again. So working out which algorithm is right on which GPU for different sizes and shapes of convolutions is vitally important, because it's I mean, some of these actually I've scaled off the graph. They go up to 20 times difference, 20 times performance difference. So it's hugely important. So what we're starting to do is we run these kind of benchmarks on each processor, create a heuristic of what should be the right algorithm for each one, and then bake it into the system so that TensorFlow now knows which algorithm to use. We also probably need to do some better kind of tiling algorithms to be able to understand these issues better. I think I've not got, yeah, no, that's the end. I've not got the numbers for matrix multiply, which is slightly harder to understand because they're not just simple different algorithms, they're different ways of tiling it and stuff like that. I've not got a good way of showing it. I mean, this is complicated enough as it is, but matrix multiply is even more complicated. But we have the same issue with the matrix multiply operations. The algorithms, the tile sizes, what works, what doesn't work, varies wildly by different GPU. It's all sorts of stupid things like if your kernel gets more optimal, it gets larger, and that gets faster until the point where you run out of registers and then performance falls off a cliff. So somehow, it's difficult to predict, like how complicated do I make it before the registers run out or before the instruction cache runs out? It's crazy stuff like that. And how do you access memory most efficiently? And for example, AMD has on-chip memory and ARM Mali entirely uses a cache that affects all of your algorithms and stuff. So it is quite a complicated thing, but it's actually really useful to be able to understand what the issue is in analyzing and optimizing for different devices. It really highlights if you want to optimize for a new device, you can't just write one convolution, you can't just write one matrix multiply and go, oh, they're really fast on the sizes that I've chosen. I also noticed today that if you see chip companies advertising really fast matrix multiply performance on certain sizes of matrix, that's not good. That is not a good test for what you're actually going to get in real deep learning. So they will often give you quite nicely large sizes, like a few thousand by a few thousand. We wiped the floor with cuBLAS on a few thousand by a few thousand. If they were all a few thousand by a few thousand, it would be dead easy for us to get performance. We wouldn't be getting those figures there. You're going to ask them, what's 8 by 3 million? That's the matrix multiply that you've got to get. What's strange sizes like that, that's what comes up. So, what's next? We need to do some further upstreaming. So like I said, most of it is in our repository. Some of it is in the Google repository. We have been working with Google on it. We're currently getting optimization, getting everything working on lots of devices. Make some quite big changes, and so getting them to accept those packages take a little bit of time. We need to open source SYCL DNN. That's something that we're doing. So we showed you that stuff. We're going to open source that. We're just getting it into a state where it is just ready for people to have a look at it and make use of it. We need to integrate SYCL BLAST. So rather than using these tensor contractions from Eigen, which is a bit nasty, it would be better to have this separate SYCL BLAST so you can separately optimize it and plug it in the same way, independently, the same way cuBLAST and cuDNN do. And more accelerator processor support, which we are doing. We are working with various companies to be able to bring this to more processor platforms. I mean, it's all standard, so it should all work. It's just a question of making sure it really does work. As engineers, we know there's lots of things that should work, but don't quite. Set up more testing. It's really important to get the testing right. You can get a version of it in, and then someone does a commit because it fixes the CUDA one and makes the CUDA one better, and then everything else breaks. And so we've got to try and stop people breaking all of the other ones. But it is all open source, it's all open standard, so it's very easy to customize. As usually in open source projects, you're welcome to contribute. You're welcome to check this out, try it out on your own, see if you can help make it go faster on certain things, make a few more of those operations work. We do have some volunteers who've been helping with this stuff. And that's it. That's the end of my presentation. I'm early on this one, but that's good because my other one is longer. But do we have any questions on the TensorFlow work before I go horribly into all of the C++ stuff? And I'll explain what SYCL is next. Maybe I should have done it the other way around. This is just to get you so excited so that you can see why I'm going into all this complicated C++ work.
Okay, so let me open the other one. This one. Oh.
Are there any questions on the TensorFlow work?
Looks like you have one.
I'll wait till the end of the cycle.
Are you? Right, okay. Okay, we'll do the second one.
He only have 30 slides, so he'll be quick. Yeah.
This one may be long, yeah. So, really what we've been trying to do in the SYCL group is standardize C++ for accelerators, because ultimately people write the code in C++. It is true, sad but true, that most accelerator code is written in CUDA, which I'm not very happy about. It would be better if it was written in an open standard that anyone could make use of, anyone could do compilers for, anyone could do research at the compiler level for. So that's why we've spent I've spent many years of my life, we've invested a lot of money in as a company, and the Khronos group has been very patient with us, and now we've got quite a lot of people involved now behind this, because people go, yeah, actually, programmers use C++, and we need to be able to write software for accelerators. All of the future performance that we're getting is going to be from accelerators. So there are a few actual options. I should explain, actually, so that you understand what this is. The C++ kernel language is something we also standardized and open sourced as a group, which adds C++ to existing OpenCL C kernels. So just so you understand what some of these terms mean, when you write an OpenCL C, your kernels are in a separate source file from your main source code. So you have some main source code, which runs on the CPU, and then your kernels, which run on your GPU or your DSP or your FPGA, are written in a separate source file. So in some ways, from a hardware point of view, it's much, much clearer to understand what's running on which device. But there are some problems with that. It's much harder to do things in C++. It's much harder to do all of the cool stuff I was showing in the previous slides about creating generic algorithms and stuff. And I'm going to show you how we do that for all sorts of things like machine vision. So a huge amount of parallel software is actually written in the single source style. So CUDA is a single source compiler. You have a single source file, has the host and the device code. OpenMP, single source file, has the host and the parallel device code. So it's actually pretty common amongst programming models for people in larger software bases to use this single source style. And then, of course, the main ISO C++ standard is single source. And they are actually defining stuff which I'm going to come to, and we're pushing them further to be able to parallelize standard C++ code. So you write standard C++ code, and you should be able to just run it on any accelerator. All standard, all from normal compilers. I've talked about that. I should miss that. If you are interested in the C++ kernel language, it actually supports the OpenCL 2.2 feature set, and the kernel language compiler is open source, so you can actually play around with it. So there are some advantages of it, and you can play around with it and run it, and it compiles down to Spear or SpearV. So this is another thing that we did, this Spear or SpearV thing, if you haven't seen it. I pushed very hard, other people pushed very hard to be able to support lots of languages on top of OpenCL. So Spear and SpearV is an intermediate representation for supporting other languages. So the SYCL design philosophy is single source, pure modern C++. And what we're trying to do is align with the direction that the ISO C++ standard is going in, but we're going to go there first. So we're pushing it first. So ISO C++ requires 2 implementations for any new feature. And they want to be able to see people using a feature in the wild before they standardize it. Whereas actually in Khronos group, we actually define standards for hardware that doesn't even exist yet. So the Khronos philosophy is much more push forward the hardware, right? Push forward the technology very fast. Whereas the ISO C++ standards body is much more conservative. They push lots of language features, but they try it a lot first. People have to prove these things in the wild first. And then there's a whole load of stuff about different versions. Sorry, I'm going to check. When am I supposed to finish this? Rado, I'm confused about the time here. Do I have to speed up or slow down? I can go slow, right, okay. I'll send it time, right, okay. Sorry, you can't see this clock. This clock is confusing me. So this is a group. It is an industry standard. There's lots of people involved in it. It's a royalty-free standard. You can go and implement it if you want. This is our current roadmap that we're targeting. I don't know why there's ghosts on it. They've got obsessed with ghosts. But original OpenCL is 2011. And SYCL 1.2 we got out in 2015. Obviously, we're still working on it. So it was quite a big job. We updated it to SYCL 1.2.1. Largely as a result of our TensorFlow work, so we discovered we had to make some changes to make things easier to port from CUDA and to bring in some real machine learning capabilities. We are stuck on quite an old C++ version. It says C++ 17. That's a lie. I think it's actually C++ 11, if I'm honest. But oh no, those are ISO standards. This one is C++ 17. But you can see the C++ standard moving forwards, and we are changing. So C++ uses the year name. SYCL versioning is going to change to use the year name as well. And we're going to bring in, yeah, that's it. No, it did say C++ 11. So we've only got C++ 11 currently. Next version is going to support C++ 17, which has the new parallel C++ stuff in. So we're going to support that officially. And then C++ 20 has a whole load of stuff that we're trying to push in, and we're going to get that into SYCL 2021. So there's two things. There's the language features coming from C++, and there's a little bit of a delay getting into SYCL, but there's all of the hardware features which we're pushing into SYCL first, and then they get into ISO C++. So I wanted to give this example of what it looks like to port existing C++ or CUDA code, basically, to SYCL, and how SYCL is different from CUDA. So on the left is the SYCL version, and on the right is the CUDA version. And at first, they look completely different. But if you look carefully, what you'll find is the logic is identical. This is the logic code here in that loop. And this is the logic code here. They're identical. The rest of it is all just boilerplate. It's all handling the communication. So if you're writing an application and you've got some really, really brilliant machine learning algorithm or whatever, it goes in here. It doesn't change. It's only the data management and stuff like that that changes. It's only the boilerplate stuff. Another difference is that CUDA has these strange language extensions that are not part of the C++ standard. It uses this global thing. It's got these angle brackets. The SYCL version, a little bit larger, a little bit more templatey, but it uses modern C++ capabilities. So it's got, this here is a lambda function. So when we write submit, and then we've got this stuff, and when we write, if you're not familiar with modern C++, this parallel for, it's not syntax, it's not a language extension. This one here in CUDA is a language extension, whereas the parallel for is not. It's just like a library, which means you can use all of your standard C++ tools on this. To run it on a GPU, you still need a special compiler, but you can have what's called a device compiler, which is what we produce, which just extracts the kernel. And so you can use Visual C++, you can use this in Visual Studio, you can use some safety qualified C++ compiler, all for the host, and then on a device you just extract the kernel and run it on the device. So anyway, you're looking at that and go, right, I have to write two versions of my code. Well, think about how a programmer would do it in a normal situation where they're trying to write code that runs on multiple devices. Well, what you actually do is you hide everything in hash ifdefs. I'm supposed to say pound ifdefs here, but I'm not going to. I'm going to stick to the English one and say hash ifdefs. So the logic code is outside it, and the ifdefs handle all of the device-specific differences, which maybe looks ugly at first, but this is how we write C++ code. This is how most people write code. But actually think about how you do this in a real application. Is you wouldn't litter your code with all these ifdefs. It would look horrible. What you would actually do is you would separate all of the device-specific stuff into the header file or some library routine that handles all of the data movement. And you'd use your device, the data movement that makes sense for you. And your CPP files would just use your library routine, and you'd stick your logic in it. There'd be no ifdefs in your C++ files. So you'd hide all the differences between CUDA and SYCL and maybe some other programming model in a header file, just as you might hide differences between Linux and Windows or 32-bit and 64-bit. So actually, it looks pretty much identical. You write the same code for multiple different systems, and you can optimize it for CUDA, you can optimize it for AMD, you can optimize it for Intel or whatever it is you want to do. Now, the other thing that we have to do to make this work is not just provide a compiler, we need to provide the ecosystem. We need to get the ecosystem around it, so you're not just getting a compiler on its own. You never really use a compiler on its own. You get a compiler with a whole load of libraries. So we need an open standard ecosystem to enable heterogeneous processing. So I've already talked about TensorFlow and SYCL Blast and SYCL DNN, but there's other stuff. There's SYCL ML, which does kind of more traditional machine learning things like support vector machines. We've got Vision CPP, which I'm just going to show you, which is a really cool library. We've got Eigen. We've also got the C++17 parallel STL. All of this is open source. So the parallel STL defined in C++17, it's the standard equivalent of thrust. You can run that on SYCL using an open source project. That open source project will run the C++ parallel STL on top of SYCL. And there's more. We've got a website called SYCL.tech, and we add videos and blog posts, and all of the different vendors involved in this put their stuff up there, and so you can stay up to date with everything that we're doing. Okay. We're doing this for performance, so I have to talk about performance. I have to talk about how we get great performance using these programming techniques. Now, the performance of AI on GPUs and any other accelerator actually relies on kernel fusion. Getting good performance on GPUs requires kernel fusion, because hand coding can never beat kernel fusion for complex algorithms. Kernel fusion fuses two kernels together, or more than two kernels together, to reduce off-chip memory bandwidth. So this is a simple graph that I show to be able to show real numbers in a very simple case so you get an idea behind it. So what we did is we took OpenCV, so that's hand-coded OpenCL code, and we ran it on an AMD GPU, and we gave it 3 trivial machine vision operations. This is something OpenVX does as well. We should do OpenVX for this as well. I should add OpenVX to graph, but it's going to look similar to some of these other things. But OpenVX does kernel fusion as well, of course. So the blue is the kernels, and the orange is the overhead. So you'll notice the overhead of moving data to and from the GPU is higher than the actual execution on the GPU. That's pretty typical. But instead of running them completely separately, we could say to OpenCV, why don't you do all 3 things? Now, OpenCV, if you do all 3 things, runs all 3 kernels, one after the other. So you can see that the kernels is that those 3 kernels together, but the overhead is less because you're not moving stuff backwards and forwards between the GPU and the CPU and stuff. So it goes faster if you say all 3 things. Now, there's this other library called Halide, which does kernel fusion. It's quite an interesting library. It's open source. It's used in Google's camera app. It does lots of really cool things. You can see that Halide, kernel time is actually the same as OpenCV. So it doesn't reduce your performance of the kernels at all, but its overhead is greater. It does do a lot more processing on the graph. But when we give Halide the whole graph, look, that kernel is only very, very slightly slower than running just 1. So this is running all 3, and that's just running 1. So that's just showing you how much on these devices, it's not the compute that matters. The compute doesn't take up you've got huge compute performance. It's your memory bandwidth. You've got to reduce your memory bandwidth, and that means keeping things on chip as much as possible. So even though Halide has awful overhead, it's still faster than OpenCV. It's still faster than writing 3 hand-coded kernels. So this complicated research library that does all sorts of amazing things is actually faster on real-world code than OpenCV because it's not a trivial benchmark. Now in SYCL, what we can do, and this is using SYCL, but it's used our library called Vision CPP, which I'm going to show next. In SYCL, we get slightly more overhead than OpenCV. So OpenCV is running on top of OpenCL, we're running on top of OpenCL, but you can see there's just a little bit of extra overhead compared with OpenCV with SYCL. But in C++, you can do kernel fusion at compile time. C++ lets you do this. I'm going to show you how to do it. It's really complicated, C++, but when you use it, it's quite simple. And so we have much less overhead. It's all done at compile time. It's all done in advance. It's just C++. It's quite simple. Less overhead than Halide, but it's got the kernel fusion of OpenCV. So this goes very fast. You can do this in CUDA, and you can do it in OpenMP. But SYCL just allows you to do it. So now what I'm going to do is I'm going to show you a more complicated example using our Vision CPP library. Now there's lots of libraries that use this technique. This technique is called a C++ embedded domain-specific language. I didn't invent it. In fact, I wasn't very happy when they invented it. I thought we should do it in the compiler. But it's a really cool technique, and it does actually work. So that's why we do it now. Lots of people have done it. The code is quite complicated to do it. So it's simple to use. You have some complicated stuff in template files. Eigen uses this technique. If you want to understand how this technique works, Eigen is not the place to start. It's really, really complicated. It's really difficult to understand. So we've written this Vision CPP library. We do it for research papers like that previous slide. There's blog posts in it. You can find it on GitHub. For some reason on GitHub, we can only get the wiki to do blog posts, so you have to click on the wiki in order to get there. But there's a whole tutorial and explains how to do it and stuff. Explains this technique. Vision CPP is a really good way of understanding how this technique works. It's kind of written much more cleanly, and it works on OpenMP. It works on SYCL. So what we want to do is we want to do a Sobel filter, like the demo I was showing there, on some Renesas hardware, which is some automotive hardware, so it's detecting the edges of the car. So what we do at the top, have you seen the auto keyword before? So the auto keyword says, I'm going to initialize a variable. I can't be bothered typing in the type of my variable. So you evaluate the expression on the right, and then you just create a variable with that type. So that means I don't have to write a type, so I don't say int or anything like that. So in has terminal, which means at the beginning or end, and it's a pixel. It's telling you the pixel format, the rows and the columns, the memory type. So we're going to use a buffer, a 2D buffer, to be able to store that memory. And then we do some slightly more complicated things. So we do a point operation. So a point operation is 1 pixel in, 1 pixel out. So we're making, is that one the grayscale one? Or it's converting to floating point format. So we don't need to know all the neighbors or anything. It's just we're doing something for a point to point. But here, we're doing a neighbor operation. So a neighbor operation says, I am going to look around. I'm going to look around the current point. So on all sorts of hardware, you're going to have to do some kind of tiling. Tiling is actually really hard. It's actually really hard to work out how the tiling works. That's why OpenVX has to do all of this stuff. It has to process your graph to do all the tiling, and there's a whole load of trade-offs about it, because if the tile gets too big, you run out of memory. It's a really, really complicated thing to do. And then maybe you've got DMA operations, or maybe you do GPU-style latency hiding. So you write a neighbor operation, then you can define it. And then you go all the way down to the end. And what happens is, as you build this up, we're building up an extremely complicated data type. So the type of this variable, the reason we don't write it out is extremely complicated. The type contains the whole expression. So the type contains our code. And then what happens is when we execute it, we provide a policy saying fuse it, and that type is actually converted into code at compile time in C++. And we don't have to write a compiler or anything. We just have to write templates. Now, the advantage of this technique is partly that you can define a graph, but what you can also do is you can define the operators yourself. So when I said point operation or neighbor operation, I'm not using predefined operators. All I'm using is predefined classes of operation. Classes of operation that affect the parallelism. The actual operator itself, I can just write it myself in standard C++. So I'm combining here where I define the operation. So if I invent a new operation, I just write it in C++. It's just normal C++. And then provide it as a parameter to this stuff here. And everything will just get worked out at compile time, and it will generate me efficient, tiled, fused kernels on the device. So this is all SYCL. What we really want to be able to do is, in some ways, we want SYCL to die. Our purpose in creating the SYCL standard is to create something that may, in the future, not exist. It may be that we don't use SYCL in the future, that we just use standard C++. Right now, that's not possible. It's not going to be possible for us to get stuff into ISO C++ without first defining SYCL and proving it, demonstrating it, optimizing it, building out this ecosystem. But our ultimate goal is to get this into ISO C++ so that anyone programming in C++ can use all of the power of a system on chip and not be restricted to just the little old CPU. So there's now a directions standard, a directions document that was created by the C++ Standards Committee defining what it is the future of ISO C++ is going to be. So what I've done is I've taken, actually it wasn't me, it was Michael who took this and gave it to me. He's the person very involved in this. But what he's done is highlighted the issues that are relevant for us. So some of these C++ language things are interesting. Like C++ is a language for defining and using lightweight abstractions. What does lightweight abstractions mean? Okay, it may be quite complicated what we've written as a language point of view, but it should go map down to the hardware with extremely little overhead. So everything I've shown you shouldn't have lots of complicated runtime calls or anything. It should all be compile time, so it maps down to extremely efficient code. But look, C++ supports building resource-constrained applications and software infrastructure. This is what C++ is for. And if we're writing small embedded devices that use phenomenal amounts of processing to do AI and vision, that's exactly what C++ should be doing. C++ supports large-scale software development. Well, yeah, that's not really anything to do with our heterogeneous stuff. I mean, it's true, but it's not really what we're about. So some of the directions are very, very relevant for us. How does the C++ Standards Committee and Group want C++ to develop? Well, there's stuff about large-scale dependable software. It's not really quite relevant to us, but improve support for high-level concurrency models. That's us. We need to help them solve this. So that's what we're doing. And then some other stuff, simplify language use, all of that stuff, major source of error. Yeah, they're all really good stuff. But we're just going to focus our responsibility on the acceleration. C++ rests on two pillars. A direct map to hardware. Initially a C idea. Direct map to hardware. It does seem to me that we're not doing a direct map to hardware if we're only programming the CPU. We have to map to all of the hardware in the system, especially as you look at the die shots of processors today, the CPUs are tiny. Right? Most of the processing power is in the other things. We have to bring C++ to those things. And zero overhead abstraction. So that's what we've got to think about with this stuff. All of the complicated abstractions that we should have shown have got to be zero overhead. We mustn't slow down our code. There's no point us adding all of these cool abstractions. Look, we've used all of these templates. If the code that comes out of it is horribly slow. And I hadn't realized this. It originally came from Simula, which is an old language that I've never actually used, but I was surprised by this. So the concrete suggestions, which we've highlighted again, is modern hardware. We need better support for modern hardware. And then then they go into the actual C++ features. So what we're having to do to get this into ISO C++, and that's what you're going to see now, is SYCL is a whole standard for programming accelerators. And we actually need to break it down into components to get it into ISO C++. So ISO C++ stuff is going to look different from SYCL. We're building it on top of SYCL, and other people are building it on top of CUDA. AMD's building it on top of HIP. There's people trying it on lots of different C++ programming models, but ultimately we're now trying to come together and standardize these things. So we've not got millions of standards going off in different directions, but we've got one thing that holds all this stuff. So we're going to have executors. We're going to have execution context and affinity support in terms of describing heterogeneous processes. There's going to be SIMD as well as executor support. More concurrency data structure. The data structures need to be able to handle concurrency. Improved atomics and memory model. the atomics and memory model has been a huge discussion on heterogeneous hardware. It's going to be a huge discussion when we get into safety analysis. It's a massive issue, the idea of what the memory model is. So yeah, let's not get into it, but it's a phenomenally difficult issue. Lock-free data structures are actually quite important for GPUs because GPUs can't do locks. And we want to turn this incomplete laundry list into a coherent set of facilities. That's the thing. It's got to all be coherent and stick together. So this is what we're working towards. So today, if you want to use the proper abstractions today in C++ 17, you can see what's missing as well. So cores, we've got threads and async. Hardware threads, we've got threads and async. With vectors, we've got parallelism TS2, which is their name for the parallel STL, basically. Atomic fences and stuff. We've kind of got parallel loops. We've got various stuff. Not all of those are actually in the ISO C++ standard. Heterogeneous offload. Look at all those things. We've got OpenCL, SYCL, HSA, OpenMP, CUDA. It's not in there. Should have written it in there. Khronos, Raja. All of these things. None of them are in the C++ standard. So the heterogeneous offload today is not actually in the ISO C++ standard. So it's kind of highlighting the gap that we've got to get to. Distributed, not actually in the C++ standard. All of those things are not in ISO C++. And so people are wanting to get big supercomputers, distributed computing across multiple systems is actually something that we need to get into ISO C++. And then the specifics of things like caches and non-uniform memory architectures is not supported. Just isn't there today. And we need to fix this because this is pretty critical to the heterogeneous systems. The memory systems are critical to performance. This is what we need to fix. So this is where the timeline looks today. So I think that C++ 20 is actually decided, even though it's not 2020. We have a pretty good idea of what's going to go in. And the heterogeneous stuff is not really going to get it in. We're going to kind of squeeze it in with parallelism 2, the second parallel STL, but it's not quite going to get it. Ranges is also, looks like that's going to get in, and we're pushing some of the heterogeneous C++ features into ranges. So the ND range of OpenCL, we can kind of fit it into ranges. Modules, I'm very worried about. I have no idea how that's going to work with some of this stuff. Concurrency stuff is where I think is where the executors are going to be. Concepts kind of partially got in, but hopefully, concepts is the thing. So I don't know. The disadvantage. I haven't told you this. The disadvantage of all these template techniques, if you've ever used them, is that error messages are awful, like completely incomprehensible and like page long. So great when it works. When it doesn't, when you get a compiler error, you get horrible errors. So the concepts is there to enable us to give the user much better error messages for these libraries. So that I think is the end of what I was presenting on C++. We can present on this for quite a long time, but it's maybe not relevant to you. But you can see that we're doing a huge amount of work today. So you could, if you're interested in how C++ is going to develop, you can write in SYCL today. It's a standard, and that will allow you to migrate to what's going to be the future C++. So the other thing that we've been doing a lot of, and it has been mentioned today, is around safety. So as I've said, all of the stuff that we've done, that I did in the past, was video game stuff. If it crashed, it wasn't, I mean, it was upsetting, my games crashed. If your game slows down a bit, it's a bit upsetting. But people do want to drive cars with their stuff. And we have to take this quite seriously and actually make sure that this is safe enough to drive a car. And I literally wrote video games where the point was to crash cars and have spectacular crashes. So we really need to make sure that this isn't happening. So I'm going to tell you what we're doing as a company and how we're involved in some of the standards bodies to do it. I always encourage people, anyone working in this area, anyone working in the automotive area, to try and get involved in this standards process because we are a little bit kind of making guesses of what the things that are important are. And one of the things that happened in Khronos, which was really noticeable, is when the Vulkan standard was defined, we thrashed around for ages with the Vulkan standard, and suddenly the game developers just went, we want this, we want it this way, we're going to tell the chip companies how to do it. And the game developers made Vulkan fantastic. It's a vastly improved system because the game developers dedicated the time to make it what they wanted. Because otherwise it's going to be a vendor-defined standard. It's going to be defined by the chip companies, and you don't want that. I shouldn't say that here, but it's true. You really want software developers involved. And so solving these safety challenges is something that's really important. I think this is in September, yeah. I've been trying to get people to fund some of this stuff for a while, but we've got that now. But we joined the MISRA C++ group, and we're starting ISO 26262 certification for some of our stuff. So we're pushing MISRA C++ to be able to support these things. I've got a better version of this slide, actually, which highlights the AutoSAR as well, the AutoSAR, adaptive auto. The latest adaptive AutoSAR is the new standard. Has got the C++ core guidelines in it, which is actually much better for MISRA for some of this parallel processing. So we may actually push that stuff as well, better. So why SYCL? So one of the interesting things that we found in our automotive customers is actually they want C++ for this. We thought that they were going to want OpenCLC, but actually, for what they want, because they want to be able to hit the market very quickly, they've all come back to us and said, actually, it's SYCL that we want. And so I think we're going to push SYCL as being the main safety-critical application development, and we may not put quite as much effort into OpenCL. I'm not sure. People may say something differently. But for us, and the issue is that SYCL is so close to CUDA. It's not identical to CUDA. It's close to CUDA. It makes it very, very similar to the existing code that they're safety qualifying. And one of the things that we found in terms of safety qualification is that people want to be able to only do it once. Now, I think that's an exaggeration. I think you are going to have to safety qualify your code on different architectures because they are different. But being able to do it as minimal as possible is really what people will be able to want. Yeah, we found that, I mean, automotive is the one that's pushing this. Automotive is really pushing some of this acceleration stuff more than anyone else. And they want to be able to use the same programming interface across all of their platforms. And current SYCL can be used for prototyping and non-safe development. But we need to be able to get to a safe language to be able to deliver it. So SYCL versus safety. Currently, the MISRA 2000, this is I've described, I'm going to go. The MISRA 2008 specification and AutoSAR rules are required. Both are on ancient C++ rules. So the original AutoSAR is on ancient C++ rules. So I think it's adaptive AutoSAR, updated guidelines do actually cover C++ 11 and C++ 14. They've done a really good job, but based on some of the MISRA 2008 ideas. So we're actually pushing those forwards. But we're also pushing forward SYCL and MISRA. Again, we do want other people involved in this. So I think the MISRA committee is really keen on some of this stuff. But the problem is that we're going into communities, in the safe communities, where most of the people there are focusing on CPUs. It's like in going into this ISO C++ groups. Most of them are focusing on CPUs. So it's very, very difficult to push some of these ideas in. So getting more people involved in pushing this stuff, particularly people who understand some of the issues, is going to be really, really important for us to be able to deliver this. And if you think, you know, there will be cars in a few years' time driving on our streets, and you may be walking on those streets, we've got to do a really, really good job of this. This is a really important thing to get right. So this is one of my pleas, is for people who understand this stuff to get involved in a standardization body to help the industry move forwards. So we need to go over how we combine SYCL with MISRA. We need to go SYCL specification purification. So all of the OpenCL and SYCL specs are full of undefined behavior. That's how you get performance. So we need to be able to get rid of all of the undefined behavior. Yep. And that's just, I'm repeating the links, but basically that's it. If you want to try it out, either compute CPP from our website, try SYCL as the open source, or you just go to ecosystem, you go to SYCL.tech, and you get the whole ecosystem, and you can download everything. And that is it. Gosh, I've got quite a bit of time left. You gave me more time than I thought. Okay. I've thrown a lot of stuff at you, haven't I? I tend to do that in these things. Do we have any questions about any of the millions of things that I've thrown at you?
An open-ended question for somebody who provides a hardware accelerator and doesn't come with the background of all this multiple software stack. What are the requirements? What do we provide to enable SYCL or C++ in terms of?
So
At the end, we need to provide the compiler for the particular instruction set. So can you elaborate maybe a little bit on how to close this gap between, we have some basic compiler, how do we fit that with the SYCL or C++ programming?
yeah, so the answer is about how you actually build this for a new processor. Yeah. So the question is, if you've designed your own processor, how do you end up with all of this complicated software running on your processor, basically? And you need both a compiler and a runtime. And that's why what we've done, we've pushed this Spear and Spear-V idea in the OpenCL group, because Spear and Spear-V, instead of writing an OpenCL C, it's a compiler intermediate representation. And that means anyone can stick their language on top. So I actually saw a presentation. I've just come from the OpenCL conference in Oxford in England. And people were using Spear-V. And one of them is the D programming language. Do you know the D programming language? It's a kind of strange programming language that includes garbage collection and memory management stuff. You can compile D to OpenCL using the Spear format. There's actually various other people doing other things. So what we did by defining this compiler intermediate representation and defining the OpenCL API, you don't need to think about the rest. The rest of it just comes. It should just work. So you should just have to do that layer. Now you may say, oh, even the Spear and Spear-V layer sounds difficult and the OpenCL API sounds difficult. But LLVM has all of those capabilities. So you take the LLVM compiler. If you do an LLVM backend, AMD have open sourced a Spear to Spear-V converter. We've open sourced, because there's a Vulkan version, compiler backends that does that. The guy who did the D programming language is open sourcing another compiler front end to be able to output all of their stuff. So in a sense, all you're doing is you're bolting all of those things together. You've got an open source OpenCL implementation in the form of, you've got several, haven't you? You've got POCL, which you can use. You've got Intel have open sourced their OpenCL, AMD have open sourced their OpenCL, so you can take some of that stuff. Obviously, if you want a commercial version, then we can provide one for you that's nicely supported. But there's all of these options to be able to do it. But you do need the API and the compiler, because that's how you achieve the single source nature, and that's how you make sure everything works, because you need to handle the data movement to the device or off. If you only have the compiler on the device, and then you don't think about how you communicate between things, then there's a massive gap. And that's what OpenCL sorts out for you. I shouldn't say it here, but we did also work on the HSA specification, which is another alternative, which also allows all of that stuff to work on top of as well. Yes?
So, continuing on the same question, so if somebody just writes the backend for the target machine in LLVM,
Yeah.
how do we guarantee that, suppose the machine has many features that are not supported by LLVM intermediate representation?
Yeah.
We just go to the LLVM development conference and
No.
add all those things?
No, you don't need to do that. No, it's quite, you can add extensions to LLVM. So you treat them as intrinsic functions in C, but you just have them intrinsic functions in the LLVM. You can add those extensions to Spear and Spear-V. You can make them look like function calls, or you can build them into Spear-V. All of these specs are specifically designed to be extended. And then if you use something like SYCL on top, you just pass it through via an intrinsic function. You just defined as an external ref as an intrinsic function. And it just goes all the way down. All of the vendors who do this stuff want to be able to support their extra features. And so it's all designed to enable you to do that. Yeah. And on the API side as well, so if you've got special stuff for memory management, you can do extensions. Khronos has specially defined procedures for defining your extensions and a whole lot of rules about it and IP rules and everything. Any more questions?
Any more questions?
Yes.
You told about the ISO 262.
Yes.
And, what's the target level of AGL?
So yes, so that's none of the standards are promising an ASIL level. So you have to define the processes and then implement to those processes. So we are targeting ASIL B in the short term. Most of our customers ask for ASIL D. I am not convinced that ASIL D is seriously possible for AI systems. Because ultimately they're statistical and ASIL D is... I think the only way that you're going to achieve ASIL D is by having multiple systems. Right? The ASIL D is at a system level, not for autonomous driving at a processor level. So ASIL D, you've got to have redundancy, and really to have proper ASIL D, you've got to have two independently designed systems. And that may mean you've got one system based on machine learning, another system based on traditional machine vision, or maybe radar or something like that, and they've got to combine their information together. That if you've only got one system, I don't think you can claim one system on its own as seriously ASIL D for these kind of things. I mean, I realize ASIL D is kind of the target that you need to get to be able to say the driver can turn around and read a book and not pay attention to the road. But I think for everyone that we've really dealt with, there may be an ASIL D monitoring system. So the ASIL D system may have to be there to monitor it, to go, hang on a minute, something's gone wrong. Because you know a GPU, if it gets hot, it throttles, as in it slows down. So if you're in hot weather, it will slow down. That's not it's reasonable in a video game. It's not reasonable in a car. So then you have to monitor that, and you may have to tell the driver. So you have a safe system that can't drive the car, but can tell the driver, you need to pay attention now because things are not working. And I think also in terms of the open standards is quite a good way of getting to ASIL D as well, because with open standards it allows different companies to do different components, and so that allows some level of independent verification between the different components.
Any other question?
Thanks, Andrew. There's so much stuff, and I
I
don't know where to start with a question. I don't know if
Yeah.
anybody else has anything. Where do I start with a question? There's so many. So what you described is a lot of stuff where, I see how the system does things for me that I currently have to do by hand, and so part of what I'm trying to figure out is how much of what I currently have to do by hand is going to be taken care of by this, and there are certain complications that we have to deal with in a modern SoC. And so the ones that are in my head are, first of all, it's this heterogeneous thing where I've got a CPU, a GPU, DSPs, might be multiple DSPs, and some special purpose hardware. And I've got to figure out how to schedule across all of those things. And I need to move the data across all of those things. And I probably have a DMA engine. Right. So I don't know, like on the SYCL, what you described there, do I write code to do all of that scheduling and management, or is somehow that taken care of? And the other one is that when I write, say, for a special purpose processor, I have tons of intrinsics. All of my kernels are just full of intrinsics. And how is this compiler, is it going to beat this, or is it going to, how do I handle all my processor that currently, in order to get the performance, I have to code with all these intrinsics?
So the first question is about the responsibility for different levels of scheduling within the system. And I think that with SYCL, and OpenCL, our responsibility is to make it easy for developers to write that stuff, but it's not our responsibility to create something that will automatically look at the whole system and work out where things go. So I don't see that as a programming model abstraction that we have a business being involved in, because we don't know your application. What we should be able to do is make it easy for people to write those kinds of schedulers. So certainly when I've seen parallel programs, what I've found is the only way to schedule it is by knowing the whole program. And actually, as you develop the program over time, you actually might move things around, because something gets more powerful, but then uses up more of the processing power. And then you go, oh, hang on a minute, I now need to move something off that processor and put it onto some other processor. And so I think what we're aiming to do with the SYCL and C++ and OpenCL standards is make it possible for you to write once and run it across all of those things, but actually making the decision of where it runs is up to either you as a programmer or some system above it. I suppose we go back to the design philosophy of C++ is it's zero overhead abstractions. So you can create the abstractions to be able to say, look, I'm going to abstract away the difference between my DSP and my CPU and my GPU, so I can write the same, but actually I still want to control it. That's the only way you get zero overhead, is giving you control over it.
Yeah, so I don't know if we're on. We were talking about OpenVX earlier today and NNEF and these. You build a graph.
Yeah.
And then you do see sort of the whole computation. So how could this help us, those of us who are writing these graph mappers or whatever you want to call them, the scheduler, leverage the stuff here, and it makes it easier for us to write the scheduler, because we do have the information about the whole program at that point. So.
Yeah, so I definitely see OpenVX is at a higher level than SYCL. SYCL is an enabler for OpenVX in that sense. So we should be allowing you to write OpenVX where you do have the whole graph, but SYCL is really a compiler. It has a notion of a graph, but it's tasks going between processors. It understands that this goes from that processor to that processor. It's not at the vision operation level. And there's no point us. We're not there to do the. We are there to do the programming model for everything, but that doesn't mean we do everything. It's the programming model to allow other people to do everything, like vision and AI.
So one of the things, though, we do have to worry about is the data movement. And
yeah.
So how does SYCL help me there?
So SYCL, yeah, so this has been a controversial issue within the SYCL group. So SYCL is designed so that you do create a runtime graph, and then it can work out where to move data when. And some people really like that about SYCL because it makes it very easy to just move it between different devices. Some devices, like you've got a discrete GPU, you've got to DMA it across. Other devices, it's all shared memory. Other devices, maybe there's on-chip memory that's very fast and stuff. So having SYCL just automatically manage that up to a point is actually quite useful. But then there's some people who hate that and say, I want to be able to control it. So that was one of the things we had to update from SYCL 1.2 to 1.2.1, was to give people manual control of that. Because there's very good reasons why you might know better than SYCL how to move your data. So you may know that you're going to need some data on a particular processor in the future, and you haven't told the SYCL runtime system that. And so you're going to go, move it now. So that by the time you then pass the task over to run on that processor, the data is there. And so that's the change that we've had to make.
So you said SYCL 1.2. I forget. But it has the hooks in there for you to be able to do that then, I guess?
Yeah,
and
so
we
it
as
always moves for you, but you can say in advance, definitely do this move now. Do it now. Don't wait for me. Don't wait until the data is needed on the processor. Do it now. And tell me when it starts and finishes. Yeah.
Sorry, the other question was about intrinsics.
Can I just answer your other except that they were some of the same questions, wasn't it? But I'll come. So your other question was about intrinsics. So always in the Khronos group, as you know, there is a standard system for adding extensions. And we just pretty much, we follow a more C++y version of that than other Khronos specs, but we handle that system, and definitely the expectation is that intrinsic should be implemented from the OpenCL level in the back end down to the processor architecture, and then SYCL should just pass them through. And there is no way that SYCL is going to automatically make use of your specific processor extension. So we have to expose that stuff to the developer so that they can make use of them. Because yes, it definitely is needed. But our intention is to design a programming model in a way where it's easy to say, oh, on this processor, we have this intrinsic, and so this algorithm is going to work much better. But not to do that automatically, just enable the programmer to do it easily and make that move around. Yeah.
So all the scheduling in SYCL is runtime, or is it actually scheduled on?
It is actually scheduled at runtime. Yeah, it's scheduled at
So
runtime.
it's within the compiled code that it's telling, okay, please go and.
No, so the compiler will just create a kernel. So, okay, so there's two things. When I showed the Vision CPP and we were fusing all of the operations together, that's compile time, because that's a single kernel. But if it's two different kernels, so if we run a kernel on a GPU and on a DSP, that's runtime.
So I have to run a runtime agent all the time.
SYCL and OpenCL both require a runtime agent, yes. Because it's almost the biggest feature of OpenCL, actually, is not the language. It's almost the fact that we've standardized the API. Because, yeah, you can write the code for the processor, and it's kind of C, or C++, but actually how you standardize communicating and synchronization, that has much more of an impact on your code. OpenCL and SYCL have standardized that, but it is a runtime system for that. There is a driver and stuff.
So SYCL is just sitting on top of
It sits on top of OpenCL. Yeah. Brad.
The question is, I'm going back to the safety critical. You mentioned somewhere about 26262. I'm wondering, how does the compiler fit in? Does compiler have to go through 26262 at some level?
That's a good question. I don't totally know the answer to that. We're still working through some of that stuff. So I think it's much easier to work out what has to happen on the runtime. So we have to be able to do fault injection, we have to track errors, we have to track things speeding up and slowing down, we have to be able to monitor the system to be able to understand is it running correctly. In ISO 26262 for the compiler, that is probably a tool confidence level. It's a slightly different thing. And the question is, how far do we need to go with the tool confidence level to be able to support some of this stuff? I am concerned that the tool confidence level that you might normally expect is not possible for these accelerator processors because they change so fast. You know, as I've often pointed out, we use CPU designs today. I mean, all the CPU designs we use today were around when I was at university. And we don't really have any new CPU designs since then. They're in active use. And so any CPU compiler could have been around for 20, 30 years, quite reasonably. Whereas any GPU or accelerator compiler is going to be developed in more of the kind of 1 to 2 year time frame. Maybe in automotive it might be 3 or 4. So just the safety qualification is just not possible at that level. And getting the performance, I don't see it as possible. So we may have to use some other techniques to be able to verify those kernels. I have spoken to people in automotive who say you don't necessarily have to validate that the compiler is always right for all programs. You just have to validate that the compiler is right for your program. So if you give developers the tools to be able to validate that your program was compiled correctly and is running correctly on the device, that may be enough for these systems.
Thank you. I have one more question.
I do have just one issue just to bring up, which is just an interesting issue, which is that if you need if everyone uses LLVM, how can you do an independence? How can you have two independent systems? LLVM is the one point of failure in safety critical systems. Anyway, yeah, sorry.
So I guess you got to split the top end and bottom end. You got to get both of them through safety process, I guess.
Yeah.
Basically, you have to treat both of them as two separate components. You take both of them separately. I think 26262 has that flexibility, right? You validate A and B separately and then say, okay, when I integrated both, it is.
To seriously get to kind of ASIL D safe enough to drive a car, you need two independent systems. That's what you really. So it's just the idea that you could just have one ASIL D system to drive a car, I think is wrong. I don't think it's possible.
No, that's
you need
not what I
two
meant.
systems.
No.
And if there's any common component between those two systems, you have a possibility of a systematic error that could affect both of them at the same time, and so you've not got redundancy. So we should be using as independent components as possible between these things. It means, in effect, no one can actually dominate it. No one can actually dominate it if we're following the safety guidelines correctly. But anyway,
Yeah, I was more thinking if I take the whole compiler stack, split it into two pieces, the front end and the back end. One goes through LLVM, the other one goes from LLVM to back. I kind of see these two are two separate components. And
Yeah.
you could take one through certification, you get two independent ones, then you can combine together. You don't have to put both of them together to get 26262 or whatever safety part is, right?
yeah.
That's one perspective, I guess.
Yeah.
So my other question is on the SYCL or C++20, can those take performance model of underlying architecture when they before converting into LLVM or SPIR-V? Does it even make sense to do that?
You definitely need to adapt. But before going to LLVM or SPIR-V, you need to take into account the underlying architecture. Yeah. Yes. That's what
How
you're
does one express those performance models for these languages?
So yeah, that's why we are doing that at the SYCL level with IFDEFs, because it's algorithmic. It's not at a compiler level. That algorithm changes. And if you do the difference between the model of a direct convolution, which is one kernel, and the IM2 curl one, which is what, 3 kernels, because you transform it into another format and then do the matrix multiply another one, and then the Winograd one, which is you transform it and then you do a bunch of batch matrix multiply, so that may be more kernels. That can't be done at the compiler level. That's runtime level. You're enqueuing different stuff. So I think it has to be done at the C++ level. I also think, however much we want to automate this, ultimately, if you've got a programmer and they've got a system and they want to make it go faster, they're going to know more than anything you as a tools developer is ever going to know. Right? They should have a profiler there to be able to analyze it, and they should go, right, I think we can make this go faster. And they can understand that more than any tool can, ultimately. Like, you want to automate as much as possible, but I think you should never get to a point where they just can't control it. But the difference between an AMD GPU and an ARM GPU is huge in terms of performance stuff when it gets to a more difficult thing. It's how many registers you've got. It's a massive difference. If you go over the number of registers, suddenly performance really falls off a cliff, and then there's a kind of grey area where it depends, and then the size of the memory. If you overuse or if you overuse the on-chip memory, then your kernel doesn't work, and if you underuse it, it goes too slow. These things are big performance differences, and there's lots of research into analysing it. I do think ultimately, a program is just going to have to go, right, I know that works. Or you just run them. I mean, so many times we've run it and gone, there's been loads of times when I've told my engineers, look, don't do that. That's stupid. It's going to run slower. You're doing the wrong thing. And they come back to me and go, it went 3 times faster. You're wrong, right? And I still don't understand why in several of them. I think they must have faked it. But these systems perform really weirdly when it actually comes to it. They're very weird, actually, and unpredictable. And you do just have to try it and just go, well, that's the result. And on a CPU, it might be 5 or 10% difference, where who cares? But once it's 3 or 4 times or more, then it matters.
All right, just a couple of slides here, and leave more time for the Q&A and wrap up here. So, so the OpenVX group here, we meet every week, and then there are 3 times a year we get together and we talk about at a face-to-face meeting at a place that moves around the globe. And so the folks who participate in these meetings drive the roadmap, and really you bring your ideas about what you want and you think it would be good for your customers, or your customers have told you they want, and things like that. So one of the things that, so we kind of use this process to go from 1.0 to 1.1 and 1.2. And now we have, as I said earlier, there's this basically a split here at 1.2 and SC, because those were developed in parallel. As I said before, we're going to combine those, so there's a single spec that covers safety critical and non-safety critical. The sort of the additional annotation here on the slide is whether it's what we would call a 1.3 or a 2.0. And really that has to do with backwards compatibility. And so a lot of times of course, this has been around for a few years now, and there are things that were added in 1.0 that when we look at them now, we go, well, does it really need to be that way, or do we need to support that? And usually the answer is yes, we have to, because if we take that out, it's not backward compatible. We want your program to run in the new version. We want to make sure that we don't take anything out. We can add stuff, no problem, but taking stuff out or changing the way an existing function works is kind of off limits. But there's because we've been doing this for a while, there's actually quite a few things where we think, we could streamline this code. We could take out some things, or we know how to figure out some things automatically, and we don't have to. So it's kind of a question for the community, for the users, as to how important is that backward compatibility, and what is it by us. And so so the things that we're looking at for a 1.3, assuming we call it a 1.3, and we can maintain this backward compatibility. And as I said, we do this merge of some things that we developed in basically the last year, a safety critical version of the spec, and also this import-export extension, which is kind of required for the safety critical. So we'll bring those things into the 1.3 spec as part of the main spec. Neural networks, as we've talked about most of the day, not all of the day, I guess, but a lot of the day is really kind of the state of the art in many applications. So increasing the amount of support we have for neural networks, we could see. So potentially we could, this kernel import extension, where you can import an entire network, could be pulled into the main spec. Another thing that we have an idea for is this NN only profile. So now that we're adding more functions, and we say, I guess we're up to 63 now, and some of those functions are fairly complicated, actually. And we count one I think of as like the color convert. The color convert is one function, but it really is about 40 functions, because you got a different function for every color you're converting from and to. So we actually, some of those functions are quite large and sophisticated, and you may not want to support all of those, actually, and you really want to do, you're focused on neural networks, you want to be able to import your neural network, you want to feed it inputs and get outputs, and maybe there's a few image processing things you want to do on the front end, but you don't want to support KLT tracking, or you don't want to support every kind of color conversion or something. Maybe there's a subset of OpenVX that you could support. And so this neural network only profile would give you at least the ability to import a neural network and feed it inputs and get the outputs, and maybe a few other things, but not maybe a lot of other things. And so that way your vendor, you as a vendor could be conformant to a profile that is less than the entire thing, but it's focused on what your customers are asking for. And you can actually there are other profiles that you could do. This is just one because it's such a hot topic, but another actually fairly hot topic is 3D reconstruction and SLAM and something like that. And you could potentially create a different profile that is supporting 3D reconstruction, and maybe you don't support neural networks or some other things that so that we can streamline it, so you can say more specific specifically what you support in your application, and then your customers can pick those things up, and they look at your implementation, and they'll know, well, they've got this and that, and that's the bit I need. So great. So the NN only profile would allow you to just pull in, say, it would be a subset of all the functions we have today, and where one of the main ones is import something. But then once you import something, as we said earlier today, the NNEF spec is just a file format. It just says you're able to import it, and what you have has been checked for correct syntax. But the syntax may be correct, but what it actually does, like if I import this network, does it behave in the way that I expect? If I give it a known input and I expect, I show it a picture of a bird, does it say bird, for example? And so nothing in the NNEF spec will actually do that for you. It will just say, I've got a network and it's well formed. But it's not going to tell me it identifies birds versus cows, okay? So we could have an extension where we say for specific network descriptions, such as NNEF or potentially others, we can import that description and we feed it an input and we get an expected output within some tolerance. So you could see a conformance suite for neural networks that say, okay, for a certain maybe subset of neural networks, or like classification networks, I'm going to have a set of classification networks that I'm going to show that I can import them, and not only can I do that, but when I present the picture, I get the right answer. And so we could have a way to say what to expect from the capabilities of an implementation of the neural network extension that we know something about, whether it's getting the right answer. And there could be groups of those for classification or semantic segmentation or things like that. So building up these conformance suites, and then you could compare, actually, in addition to just showing that they're get the right answer, you could even, well, if you get the conformance suite from multiple vendors, you could compare performance as well. You could say, look, I know what these networks are supposed to do, and I see you're getting the right answer, but I can also, put the stopwatch on you. So you can evaluate across vendors that way. And so, and then for 1.3 plus, it could be 1.3, it could be 2.0, or it could be 1.4 if we but really there's a lot of things that have been discussed in the working group, and getting feedback from the community, from people who are users, potential users, developers. What is it that's missing? So some of the things that have been discussed is more feature detectors. So we have a set of feature detectors in there, but there's many. And so could we add some more? And would we add them, say, as the main spec, where with the main spec, you're saying, in order to get the logo, to say you're conformant, you have to implement everything in the main spec. But maybe we have profiles, as I was describing before, or maybe there's just extensions where we just say, okay, here's a new feature detector that we don't have in the main spec, and you can be conformant to that extension, and it's just maybe that one feature detector. And maybe we have different extensions for a collection of feature detectors. And again, we want to make sure that we're not fragmenting the ecosystem too much. So you're always trying to strike a balance, but it could be getting feedback from interested developers like you guys would help us drive whether it would be a feature set or an extension or in the main spec, because damn it, I got to have this feature detector. Stereo vision is another one that's is still, there is stereo for neural networks, but there's actually really good stereo that's sort of using traditional vision, and we could add some support for those particular stereo algorithms. And SLAM, sort of more of 3D, so as you move your camera through the environment, one is you could get some good visual odometry. So we could start with just say, you know, I need to know where the camera is as I move it around based on what I'm seeing, and have that be an extension, and then go to the next level where you're actually building up a model of your environment as you do that based on what you see and based on doing the stereo from structure from motion kind of algorithms. So we could add some more for that, and maybe that's a profile where you add it not necessarily in the main spec, but you say, look, if I want to do SLAM, I have this subset of functions that I need to be able to do it. And then this API framework refinement, this is where I was talking about there are things where, you know, maybe it would be 2.0 instead of 1.3, where we would break backward compatibility. We'd take things out. One of the things that we've talked about a bit in the working group is the idea of, well, we have virtual images, and when you want something to be a virtual image, you say, I make this virtual, and then the system can optimize it out. It can say, oh, well, the user, because by declaring this thing virtual, the user has promised that they're never going to try and access it, so I can I don't have to actually create it if I can figure out a way to get around that. Well, it could be that we could just make virtual be the default. So instead of having to say for every image whether or not it's virtual or real, we just say virtual is the default, and only when you go to access it later, you have to say I'm going to access this thing. So it's actually a change in the API where, you know, some APIs would go away and a few new ones would come in to sort of give you that functionality. And so is it worth it to change the API and make it potentially easier to use and potentially easier to optimize without, but breaking backward compatibility. So that's some of the simplification I would talk about. And I guess I've talked about the profiles and subsets. Flow control is another one where we've introduced flow control with conditional execution. So if you have some part of the graph that maybe two parts of the graph where you, depending on what you compute at the beginning, you can decide which of those subgraphs you want to actually execute, and the other one you just wouldn't. So we have that, and maybe there's more flow control that we want to be able to support, such as looping, where you say, well, actually that bit of graph I wanted to do n times, or keep doing it until something happens, that sort of thing. So we could add more framework for that, just to increase the capabilities and flexibilities of the things that you can express with the graph. And, you know, as we say, it's driven by community participation. If Khronos is open, all of your any company can join, or even individuals can join. There's different membership levels at which you can join, and all you have to do is join and become active in the community. Once you go to the web page at Khronos and you say, you can see all the specs there, and there's mailing lists for each one. Somebody asked me earlier, so if I'm interested in OpenVX or NNEF, how do I start participating? And so what you do is you or your company joins Khronos, and then you get an account, and you basically, once your company joins, then all you have to do is go to the website with and register with an email address with your company email address, and then you have an account. And then there's a bunch of mailing lists, and you can just go to the mailing list and you can subscribe to that mailing list for OpenVX or NNEF or SYCL, and you can start getting the announcements about when the meetings are. We have meetings every week, calls. You can start participating in that, and that's one way to join. And of course, you can also send messages to those, say, you know, I have an idea about or I have a problem that I need solved, and how can you help me, or what this is my recommendation about how OpenVX could be better, and participate and help us drive it that way. And that's all I have for today. Any questions or comments or thoughts about the roadmap?
You want to mention about forum? OpenVX forum, people can post questions.
Oh yeah. So actually, we should put. Do we have a link on that to some of the materials? But there is a forum where you can just go to the forum webpage, and there's for all of the specs. There's a sub forum, and you can ask questions there. Those are monitored by the working groups, so you can ask your questions there, and then, hopefully within a couple of days, you'll get at least some response. We generally try to get a quick response, but then also, because we have these working group meetings every week, we'll discuss if we have a particularly sticky question, one that we want to really kind of chew over with the group, we'll talk about it in the working group and then get back to you after that. So,
I don't know if it's the right place to ask this question. So is there any overlap between OpenXR and OpenVX?
At the moment, so I have been to like one OpenXR meeting, and really it's mostly focused on VR right now, like the display side and maybe some of the tracking, but not camera so much. And so my request to the OpenXR group is, as soon as you start throwing cameras in there, make sure you talk to us, because there will be overlap at that point. And so, yeah, as of today, not so much, but we do want to try and work together. So, for example, the OpenVX group and the NNEF group and the OpenCL group and the SYCL group, we talk to each other and try and leverage what each other is doing. But as of today, it's pretty much on the display side what they're doing on OpenXR.
Thank you.
Yeah, I think I want to add one more thing to that is, if you look at you put the diagram, right, on OpenX, if you see the augmented reality VR, on one side you have the OpenXR, which is kind of to be able for the display and haptic control. You're interacting with the environment. OpenVX is you sense the environment. So one is going out, the other one is coming in, information.
Yeah, but in XR they say that they are extending support for AR.
Yeah, the support for AR means that is still for display part.
Okay.
As of today.
Okay.
There's if you're going to do a good job of doing the display, even you want to do some prediction, like as the person moves their head, you want to render for where their head will be by the time you show them the frame buffer. So you can do that with one good way to do that is with sensors, with inertial sensors. Another good way is to do visual odometry and be able to track those things. So that's one thing that's already sort of they're wrestling with in the OpenXR group. But then when you want to do actually augmented reality, so I want to see that there's a table there and I want to put a little character on it or something like that, then that's when it'll get sort of deeper in terms of the interaction between us. We haven't got that far. Yeah,
So in the product, do you see that both OpenVX and OpenXR are used simultaneously?
Yeah, I see.
let's say
Yeah, you would potentially be using both APIs in the same product when you're doing your application. Yeah.
Okay. Thank you.